like the moment I start streaming, everything just slows down. All right. So, moving on with the schematic review of my motor drive, which you can see in the background here. And I'm working through the list, I think. Let's see. So I got 576 lines. So 575 lines without the first line, which is the header. Anyway, I'm not even halfway, but I have to go through every single component and see if it makes sense to have the component on the schematic. As you've seen in the previous video, it's very common that I find something that I need to fix when I go through every single component. So I'm going to go through the components, and then after I'm done with the component review, I'm going to go through every single label, and I'm going to make sure that all the labels are connected where they should be. But for now, the focus is on the components. So I'm going to go to C5 now. Let's see where the C5 capacitor is on the schematic. So find C5. C5 is the VCAP. Now, the VCAP is recommended to have capacitance of 2.2 microfarads, and that's specified in the datasheet. Let's go and have a look. So we have the STM32 datasheet here. I think, yeah, this is the reference manual. So VCAP. Let's see what this manual says about VCAP. The voltage regulator, let's see, so embedded linear voltage regulator supplies all digital circuitries except for the backup domain and standby circuitry. It requires two capacitors, VCAP 1 and VCAP 2, in all packages, available in all packages. Specific pins must be connected to either VSS or VDD to activate and deactivate the voltage regulator. These pins depend on the package. So I think there is a pin somewhere here. Let's see. Let's find out what pin. Yeah, there we go. So PDR on. I've connected it to VDD 3v3. Let's see. Is there a recommendation for the capacitances? Let's see if there is any description of this. Maybe it's in the datasheet. So this is a reference manual, and sometimes certain things are in the datasheet, certain things are in the reference manual. Usually the reference manual is focused on anything that concerns programming, whereas the datasheet, yeah, actually I should have the datasheet here. Let's see. Got the datasheet here. And the datasheet is about the electrical stuff. So we can see here VCAP. Let's see. Regulator on. Internal voltage in VCAP 1, 2. Let's see. So this is power scale. Does it say what the capacitance should be? Yeah, there we go. VCAP 1 and 2, external capacitor. 2.2 microfarads, okay, right. So if we are bypassing the voltage regulator, then we should not have 2.2 microfarad capacitors there. But anyway, I'm using the voltage regulator as far as I know. I have to double check. Let's see. Where is... Yeah, let's see. Regulator on. On packages embedding bypass reg pin, the regulator is enabled by holding bypass reg low. Okay, on all other packages the regulator is always enabled. I think the bypass reg pin is only available on the BGA packages. Let's see. Yeah, so they're available on the BGA and the QFP 176. So on the 144, which I'm using, the regulator is always on. Right. Internal reset on is if PDR on set to VDD, which it is in my schematic. So this is correct. So we can say that both C5 and C6 are green. Let's see, C5 and C6. I can make them green. Moving on to C50. C50 is... Where is C50? C50. Right, C50 is the capacitor that I know where it's supposed to go. I added it because I realized there was some pin that needed it. But now I don't really know which pin that was. Could that have been the VBAT pin? Or maybe it was the VREF plus pin or something. So I'm not really sure where this is supposed to be. So we got 3, 6, 3, 3. Right, so we got 12 capacitors that go to each one of these pins. But then we have VDDA and VREF. Now, what I realized though is that, oh, by the way, this needs to be fixed. What I realized is that I don't have any bypass capacitors on the VDDA and VREF, which I should have. So I'm going to add that. And I'm probably going to remove the connections here. But first I'm going to fix this one. While I'm at it, I'm going to hide the datasheet field. Let's see. Okay. So C50 will go, so we can make C50 and C something else. What would that be? Annotate this. C32. So we can have C50 and C32 connected to C. The ground can be connected, but then we make this VREF. Actually, I don't like this. I don't like the fact that I'm using a label that's specific to a certain chip. Instead, I'll just drag this here. Even though this is a little bit ugly, it's a better, more clear way to connect the capacitors there. Okay, so we can green C50 and C32 is probably already green because I removed it. Yeah, C32 there, C50 goes green, and C52 is the next one. Oh, wait a minute. So C50 was 402. It was the same cup that I used everywhere else there, yeah. So C52. 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 That's one of the output capacitors here. 22 microfarads, 10 volts. So this is a 5 volt thingy. So 52 and 55. Let's see. Wow, that's 22 microfarads, 10 volts, and it's a 805 capacitor. Does it have to be 805? Maybe it doesn't have to be 805. Who knows? We should find out. Let's see. Am I loading the page? No? Come on. Okay, so this one is, there's 21,000 of them, and it's an 805, and we can do like this. So I'm going to go ahead and select the capacitance, and I'm going to show similar. It could very well be that, because it's such a high capacitance for a small part, it could be that the packages are bigger. So yeah, the smallest one is 603. So we pick the 603. Oh, actually no, I'm not going to do that. I'm just going to sort them by price. And yeah, I have to pick the voltages also. So we need like 10 or, let's see, anything above 10 volts, and probably up to 50 volts. Anything bigger than that is going to be bigger packages. It looks like that one was the cheapest one. Yeah, so that's a 805, 10 volt, and yes, that's pretty much what I have to use. Okay, so C52, 55, and I need to just double check the fact that it is 805. It's good, and yeah, it is 10 volts. So 52, 55 goes green, and then there is 53. C53 is one of the capacitors that goes on the LED driver, and they're 2.2 16 volts. Let's see if that's correct. So LP, let's see, what is it? LP55231. So I'm gonna go here, and I'm gonna find this chip. LP, was it 55? 231. And which one was it? Just to double check. It was no PB. SQX, no PB. SQX, no PB. Right, so they're using smaller capacitors, but I used the 2.2 microfarad because I'm using them elsewhere. So I need to just double check that this is like if there is any limit on what can be used. Usually there isn't, but there could be. You know, you never know. So flying capacitor. Flying capacitor. A capacitor that can fly. Where did it fly away? Can we find the flying capacitor? Is there a section that deals with flying capacitors? Flying capacitor. Funny, if I search for it, I get nothing. Did I spell it wrong? Flying capacitor. Come on. Capacitor. What the fuck? You gotta be kidding me. Why is it not? Like, I can't search for it. That's ridiculous. Come on. Why? Why can I not search for it? Huh. Interesting. Let's see if there is any section that deals with this. Maybe if I save this, then I could. Oh, I can just open it with document viewer. Maybe I can search from the document viewer. I don't know. Let's see. Flying capacitor. Oh, there is this weird little character there in the middle, which seems to mess things up. Okay, at least this works better. At least we found a few flying capacitors here. Both flying capacitors are charged from input voltage. Let's see. So I suppose, like, does this mean that it's 4.5 volts? Right. Oh, that's output voltage. It's supposed to be 4.5 volts. Okay. So I suppose there is no. Let's see. Must always be used. These capacitors are small, inexpensive, and very low current series resistance. And capacitors with are preferred for use, which I'm using. These capacitors have the tight capacitance tolerance. Let's say capacitors. Oh, that's interesting. Proper operation is necessary to have at least 0.24 microfarad of the capacitance for each of the flying capacitors, which is good. If we use 2.2 microfarads, then we have plenty of room there. So the higher the value of C out, the lower the output ripple's magnitude. For proper operation is recommended to have at least half of microfarad under all operating conditions. Well, that's fine. So voltage rating they're using is 10 volts, and that's what I'm using as well. So we can use the 2.2 microfarad capacitors, C53 and 56. We have 16 volts there, actually, not 10 volts. Which brings me to, do we have 2.2 microfarads 10 volts anywhere? No, we have 22 microfarads 10 volts. And 2.2 is pretty much 16 volts everywhere. Let's see. So I'm just gonna green those capacitors, and then I'm gonna search for any 53, 56. I'm just gonna do one thing at a time. So 53, 56. I'm gonna green those, and I want to find if there is anything that's 2.2 microfarads, but of a different voltage rating. Oh crap! Wait, what the hell is this? Ooh, I see. I see. Okay. So, ew. How do I select everything that's to the side here? I think what I did I think what I did was I kind of pasted it. I think I selected, right, so what I did was I selected the rows, and then I pasted onto that space, which actually pasted multiple copies. So that should be better, that should be faster as well. Okay. Can we search just one column? Yeah, 16 volts, 16 volts, 16 volts, 16 volts. 16 volts, 16 volts, 16 volts, 16 volts, 16 volts, 16 volts. Everything is 16 volts, which is good. Besides these two, so we have 100 volts, but that's fine. So these ones, they need to be 100 volts. Yeah. Okay, that's fine. So C54 then. Let's go to C54. C54 is on the UX connector, and the UX connector has a separate LDO that feeds the 3.3 volts output here. Now, I think it would make sense it would make sense to add a diode here, because we don't want under any circumstances to power this, to have any power going out here, which could be, there could be a design flaw in some card that is added as expansion, where you would have power going both ways. Like if this is connected to some to the same line, for example, like or if you have, for example, a USB power, and then that is fed to a 3.3 volts regulator, and then the other board is kind of powered both from USB and through this UX connector, then there could actually be current flowing backwards here. We don't want that. There is ways to protect the regulator. We could have a diode, for example, coming from the back here and to the front. So normally it wouldn't conduct, but then it would conduct if it's if the voltage on the output is pushed above the input voltage, which is kind of like it's a way to protect the regulator. But I think the better way here would be to kind of make sure that we have. Or actually, let's see here. What could we do? TLB 5533. So C54 is green. I'm gonna green that one. C54 is green. And while I'm at it, I'm gonna find out. I don't want to place a Schottky diode here, because I don't want to drop this 3.3 volts. I want to instead have some other solution. Let's see. I'm thinking maybe to put a MOSFET. Let's see what we can do. We could wire up the MOSFET like this. Let's see. Do we have any MOSFETs here besides the ones that we are using? Got a MOSFET there. Yeah. So this one is using P channel, and this one is using N channel. So we would need a P channel. Okay. I mean, this seems like a decent solution, because we're not looking to have any significant currents flowing. So using a PMOS, this would be good. Let's see what people have to say. I have lost quite a Nah, I don't like this idea. This is okay for like a voltmeter, but for anything where we are going to be driving a circuit, this is not okay. Let's see what people have to say about this. Oh, that could be an interesting thing. So, application note from the TI. So we could basically just have a MOSFET like that. So, very low resistance, ideal for finding disconnect protection, minimal loss. So MOSFET in ground path and PMOS on the high side path. In each circuit, the flex body diode is oriented in the direction from the current flow. Right. So this is quite this kind of does a double thing to a diode. So even if the MOSFET is off, the current will flow here, but there's gonna be a voltage drop. But then when the MOSFET is on, there will be a very low resistance here. Yeah, and if it's but wait a minute. So this is I think this will actually also lead current backwards. So this is just a reverse polarity protection. I'm not sure if this will actually lead current backwards. I want to check this. I want to see what happens. Let's see what happens if this is used. So I'm gonna start LTSpice, and I'm gonna do a little test. We'll see what types of currents flow. So let's just make a simple quick schematic here. I'm going to put an NMOS, or rather PMOS, and let's see, I'll rotate it like, I suppose like this, and I'm going to add a voltage source, voltage source there, and voltage source and the voltage source there, and then I'm gonna have a load here, which will just be a resistor. So let's see, I can simulate the load, and let's set this to some PMOS. Can we set this to PMOS? Pick the MOSFET. And we can pick something that's, so let's see, so that's low resistance. Maybe we can go like after VDS, something that is small. It's gonna have a very small VDS, 12 IRF. Okay, let's just go with something like that. Can pick a a different MOSFET later. So this will go like this, and like this, and like this, and like, I'm gonna just put ground symbols there. So, setting the voltage here, this would be 3v3, and this would be, let's make it like 120 ohms, and this can be 4. Let's see what happens here. So we can make this, no, like Control Z doesn't work. It's F9 is undo. Ridiculous. This is so ridiculous. It's the worst UI I've ever used for laying out a schematic. Let's see what this does. Stop time. I'm going to do a transient analysis. I got some current flowing there. What we would like to see here is actually, I'm going to put a resistor here so that, in fact, this would be like, you can make this 10 ohms. We can see the current flowing, or actually just 1 ohm. And we can see the current flowing, whether it goes backwards or forwards. And we can put this to like series resistance of 10 ohms. And this one as well. So that we have imperfect power sources, which all power sources are, but they usually have lower resistance. But yeah, 10 ohms is okay, just to see an effect. And then we can just see here. So we got 90 milliamps flowing that way. And here we have 29 milliamps. And what is the voltage here? Let's see. 3.5 volts. Yeah, so this doesn't really work. This doesn't provide the type of effect that I'd like to see. So I want to have current flowing here, only in the other direction. Let's see here. What if we delete this and simulate again? Do we get? Yeah, we get minus 25 milliamps, and this becomes 3 volts. Yeah. And this current then is minus 25 milliamps. And if we undo this and run this again, get current is 19 milliamps. So now the current is flowing backwards. If we make this 2 volts, then I think we'll get minus 71 milliamps. So there is a bit of an effect there. The thing is, I don't want to use an ideal diode here. So either I'll just leave it as is and just mark it as a 3.3 volts output, or I'll have to come up with some solution to this. So let's see if we have ideal diode. There's actually, we can just search for ideal diode here. There's going to be some products here that will give us ideal diode. Oh, it's actually, let's see. I don't think the search went through. So, there's quite a few of them. Let's see what we can get that's cheap. Ideal diode. No, that's TDS. Current sense ideal diode. The thing is that those things are rather expensive for the limited amount of functionality that they give. So using something like this is good if you want to like prevent any backpowering, but I think there should be better ways. I don't like this idea of yeah, I don't like this idea of using something that costs so much. Let's see if we can find anything for LDO reverse current protection. Actually, what I could do is I could go to this LDO, to the data sheet of this LDO. Where's this LDO? Where's the UX? Let's see. There. I can go to the data sheet of this LDO, TLV5533, and I could search for whether they mention anything about, let's see, TLV5533. No? Really? 5533. Nothing. That's interesting. Is there nothing? No data sheet? TLV 75533. So TLV 75533. Yeah. Okay, so this was actually wrong, which means I have to edit the symbol. I want to fix any issues that I directly see. I don't want to wait until I go to this, until I reach this chip in the review. I want to fix them right away. Then when I reach this chip as part of my review, I'm going to look for other issues. So let's see. I'm going to close this one, save that one, and then I'm going to edit this to to point to the 75533. That's better. Okay. Reverse current. It would be either reverse current or like sync capability. Ultra small log constant current, LDO. Let's see. Let's go to page 4. Thermal, yeah, let's see. There are LDOs with reverse current protection. Yeah. Although, yeah, when V out becomes higher than V in, it's actually it's actually not a problem here, because let's see. Because that will never happen. It's more of what I'm more worried about is whether there is any effect of connecting two power sources directly together, and whether this LDO will suffer from that, or whether it will just let's see. Yeah, they're basically trying to sell this reverse current protection. Let's see what people think about this. Okay. Yeah, so the main issue is if there will be, so if we're not powering, if the input voltage is lower than the output voltage, so what can happen is that basically what will happen is that if we have, oh, what is this? God damn it. TLV 533 is not found in cache. Okay, I think I used it somewhere else. So let's see. I think it's used for the ref supply. Come on. God damn it. Let's see. TLV 533. Let's see if we find it somewhere. Yeah, gotta zoom in first. No item found. Okay. Well, what's this bullshit about the cache? Like, what if I move this and I put it back and then I save? Am I gonna get the same error? Let's see. God damn it. Create a single library cache. Like, what the hell? So is this saved or not? Is this saved or not? Wait. This is weird. Okay. This one is supposed to be right. Yeah, this is weird. What we could do, okay, this is U20, so I'm gonna just delete it, and I'm gonna add another, I'm gonna add U20, this, TLV. Yeah, this is probably gonna work better. I'll set this to U20 directly, and now I should be able to save. No? Really? What the hell? What the hell? Oh, yeah. Of course. There we go. That's the one that's causing the trouble. That's the one. That's the one. So, this should maybe work. Yeah, this worked. Okay, everything is saved. Let's see. The situation that can arise here is that this one is connected to some power supply which doesn't turn off when VDD 5 volt turns off, right? The issue here is that when input goes lower than the output, which it will when this pin contains some voltage, then there will be current flowing backwards here, which is not good. And that current is going to actually power things that are on the 5 volt bus, but it will be like 3.3 volts, so it's going to be, it can be a large current. So we don't want that. We want to make sure that this diode doesn't get overloaded. So I think that I think we can actually solve this problem just by putting a diode here, going in reverse here. So something that can lead more than the internal diode of this LDO. I'm gonna see if I can. Let's see. This could it be this one? No. Which one was it? There, TLV. Yeah. So this should be the data sheet. So is there any specification for the current? Output current, output capacitor, reverse current. Is there anything in terms of reverse current? Right. Application information continued. Nice. So, as with most LDOs, excessive reverse current can damage this device. Reverse current flows through the body diode and passes element to the static point. Okay. Conditions where reverse current can occur are outlined in this section, all of which can exceed the absolute maximum rating. V out more than V in plus 0.3 volts. Okay. Ah. Yeah, so we definitely need to have like this circuit is going to be a problem even if nothing is connected here, because we have a capacitor here which will charge, and then when the 5-volt supply dies, this capacitor is going to discharge through this LDO. So we don't want that. That's bad. That's going to just destroy this LDO eventually. So we need to fix this. I'm going to move this down here. I'm going to see if I can find any diode that I can use here. I think the BAT54 is usable, but maybe I can find something. Do I have anything that's like a single diode? Let's see. Let's check the list here. Is there any diodes? So we have BAT54S and we have BAT54D27. Let's see. So D27. Let's see. Okay. I can just use this diode. I'm going to copy it. I'm going to place it on the path of the current flow here. So that's it. Let's see. Oh, come on. Yeah. There we go. Remove this one a little bit to the side there. Align everything. Place wire there and wire there. Excellent. Alright, so when the power goes, this LDO is now protected. I like BAT54s. They have very low dropout voltage, or like very low voltage drop, sorry. So they're usable in most cases. Now I think it's I think the diode is around like 200 milliamps or something like that. So it could actually be too small for the job. Can we open the data sheet and see? I'm just going to make a quick look at the data sheet here. I'm not going to bring it up on the screen. Let's see. where is the current? Yeah, it's 200 milliamps. Okay. So that could be a problem, but I think it's still much better than the internal diode of this LDO. Let's see if we have, yeah. I think this is a good balance between cost, size, and utility value. So I think I'm gonna go with this diode here, but it's good to keep in mind that this could be an issue if it's back powered, or if the current here actually becomes larger than 200 milliamps, then this diode can get hot. But under normal circumstances, I think the capacitor will discharge fairly quickly. Any current flow would be hopefully low enough. But I'm not quite sure what maximum value of the current would be in this case. It's kind of hard to tell. Because everything will be powered basically through this capacitor, from this capacitor, when this capacitor is charged. So yeah, this is a little bit of a question mark for now, but it's still better than not having it here. So I'm going to annotate this diode, annotate schematic, D32. I guess D32 is probably, yeah, it's going to end up there, but yeah. This is not going to be in the review, but we can say that it's pretty much greened now. Yeah, so this one stays there. Now, C54 was the last capacitor that I've looked at. Let's move on with the capacitors. Next we have C57. Actually, let me just have a look here. So this is another place where I use this LDO. Yeah, but in this case, like this is a bit different, because in this case there will always be load connected to the output. So this capacitor will discharge very quickly through the microcontroller and through anything that's connected to the 3-to-3. Let's see. So this is, in this case, it's probably not a problem. In this case, it's not expected that there will be any significant reverse current flow. So I'm going to leave it as is. And I'm going to go ahead and look at C57. We've got C57. Where's this cross? Where's the goddamn cross? There. It's V out. So that's 16 volts. C57. In terms of footprint, it's fine, but in terms of the capacitance, we have to check the datasheet. Let's open up the LP55 there. Let's see. V out. V out 2 point. Let's see. Oh, I suppose V out is like 4.5 volts or something. Yeah. So V out is the, yeah. Okay. This seems to be reasonable. Let's see. So 16 volts is fine for that. This would be green. And C58, that's the one I was looking at before. C58 was on the regulator, I think. 58. Yeah. 22 microfarads. 10 volts. Yeah. Can leave this. C58 is green. C59. Oh, God damn it, come on. Like this. C59 is the VL on the max. Right, so VL is the interface voltage. Yeah, that's fine. And we have a C61 there as well. That can be fine as well. So 51, 59, and 61. And then there is another part of this. So let's see here. So 60 and 62. So all of these are green. Next we have C63, which is for some reason a 100 volt capacitor. So this could be wrong. This is okay. Where is it? Where is the cross? Can you see the cross? Where is the cross? I don't see it. Zoom in. Yeah, there we go. Okay. So this is absolutely unnecessary. This is bullshit. This is supposed to be, let's see, like this will never exceed 3.3 volts in this case. So we really need to well, actually here I just realized that maybe this should actually have an extra protection diode. There should be a TVS or a Zener like this, which we actually have. So yeah, which we have on the VDD333, but in terms of protecting this input directly, I think we could benefit from that actually, because there could be cases where there is a bad solder joint, for example, between on this resistor. So what you get is you get VMOT on this line, and having an extra diode there is a rather good idea, I think. So you can have that diode there, and move this out, yeah, and this capacitor is going to be replaced. So this would be 50 volts, 402. 50 volts and 402. Validate, symbol is valid, update field values. Yep. 402. That's better. C63 is okay. This is why I think it's important to review every single component. I mean, such things, it's really bad if, like, it's really unfortunate if this would be a 603 resistor. And discovering this when making the layout, it just prompts one to go back to the schematic, and that can cause even more errors. So finding such bugs before moving on to the layout is paramount, I think. Very important. So C64. Let's go to C64. C64 is plus minus 40 volts is going to be maximum voltage here is plus minus 40 volts. So 64, 65, and 66, we can green them right away. 67, 68, and that's the second one, I think. Here, it's probably here, yeah. 60, let's see. 67, 68, 69. Green them as well. C7. C7 is on VDD 5 volts, and we've got this one. Let's see. This is for the analog inputs. So yeah, that's fine. Can have 2.2, 16 volts. 402. Good. And we've got C70. That's fine. And there's a lot of op-amps here actually that that are going to be unused. Yeah, we're gonna have to, when I'm gonna review the U26, actually let's check this. So let's go to let's follow the same approach. If I see anything that's potential problem, I'm gonna fix it right away. So TLV, actually let's do like this. Let's see, there's no data sheet. Damn it. TLV 2474. So I'm curious what it says about unused sections. If they should be somehow connected to ground, or if they can be just left floating. It's important to connect. If they, let's see what datasheet says. First of all, so unused. Can we get something unused? Unused. No. Should be. Let's see. Driving capacity, offset voltage. Okay, 6.8 microfarads in parallel with 100. So what to do with the unused sections? Doesn't say anything. Maybe it says something. This section is huge. Let's see. Or like unused inputs, maybe. See if we find anything generic. Application note from TI. Right. Proper implementation of unused op-amps. Split supply rail. Proper implementation of unused op-amps. Single supply. Okay, right. Huh. It's pretty cool. What is this? Improperly terminating unused op-amp pins has the potential to lead to degraded op-amp the op-amp or system performance. Oh, goddamn! What is that? Leaving either the input or output pins floating will create unexpected voltage shifts, which lead to unpredictable behavior. Connecting a single supply amplifier in a buffer configuration while grounding the non-inverting input will cause the output stage to saturate, potentially causing increased current consumption above the maximum quiescent current and unwanted dissipation. This configuration can also cause unpredictable signal corruption induced by crosstalk interaction between the used and unused op-amps. So, electrical overstress. Yeah, pretty cool. The unused sections, I'll have to wire them up to 10K resistors. So let's go ahead and do this. So U26, I don't think I'm using U26 for anything. Let's see. Yeah, U26, and we're gonna search. Ooh. Okay, so I'm actually using it. Let's see, this gets a little messy. So we got U26A is used, B, C, D. And then we have A, 33, A, B, oh, God damn it. And that's like U35A. So U35A, U35 in general. So this is bullshit. This is total bullshit here. Let's do like this. So let's make sure that U26 is going to be connected only to the voltage sensing, and then what we do here is we change this. So we have 33 and 35. So this would be, let's see. Is it, okay. So let's change this to U33. Yeah. And this one 33, and that one is 33 already. Yeah. So this would be A, and this would be B, and this would be C, and this would be D, and this would be 35. So let's change this one. Field reference 35. Field reference 35. 35. So 35A, 35B, 35C, and 35D. Cool. Okay. Now, going back to this op-amp that we have for the voltage sensing, we have to take good care of actually, let's see, 16A, B, C, D, yeah, good. We need to take good care to connect the unused sections. So where was it? Here. So we got 26A, and we can place some 26B, and like this. Okay, and this would be B, C, and D. And the reference would be 26. And reference here 26. And reference here 26. Okay, that looks better. So I'm gonna wire these. I'm gonna wire these up using 10K resistors. Let's see. Got a 10K resistor there. I'm gonna copy it, and I'm gonna just connect them like this. Yeah. Move it slightly to the top there. Okay, now what they do here is you basically have the ground pins grounded, and you then have the resistors, yeah, and it's just feedback. Yeah, this is a bit ugly. I agree. I highly agree that this is very ugly. Okay, put it there. Okay, I'm gonna connect this. I'm gonna connect this one there. Or actually, no. This, okay, let's do like this. Control Z, Control Z. I'm gonna copy this one here. And this one here. And this one will go up here. And this one down here. Okay, this is ridiculous. Okay, this is the wiring of unused sections in an op-amp. So many components just for the sake of having an op-amp. Okay. Yep. And then this is going to be white ground. And a few more resistors here. This is so not pretty. So not pretty. I don't like this. I don't like this at all. I think this is ugly. This is one of those things that's ugly as fuck. Let's see. I'm gonna go like this. Okay. Let's see. Redo. Control Y. Okay. I'm gonna move this one to the side here and have. Let's see. Delete the wire there. Okay, cool. Now, now I can just connect. I think I'll delete that one, and then I will just copy this. No, come on. Or rather, I mean, I'll just move it. I'll actually move it here, and then move this one. Move this one here, so that we have a bit more space here. And this one will go here, and then this one will go here. Okay, cool. And then just the last detail here to place these two resistors here. So and this actually fits nicely. I'm gonna move this one field value. Move it up there. And then I have, let's see, and this will go to VDD323, and then this will just go like this. Cool. Ah, this is bad. Let's delete this wire. Yep. It would be so nice if KiCad had some way of having this review list directly in KiCad, so that it would be possible to mark components as reviewed, and not lose that information if I were to generate a new list, because I would have to essentially merge the list. I'd have to write a Python script to merge the list when I have added new components, and when I have a whole bunch of new references which I haven't reviewed yet. But I still want to keep my old review, the components that I've already reviewed. So this is a bit of a hassle. Oh no, this would be wire. Make this wire. Yep. And another wire there. So this looks good, I think. And I'm just gonna add a note here that this is unused sections. I think this, yeah, this would be very big. So this would be better to make it 1. Make this here. So, cool. Now, moving on, let's just annotate this. One last thing. So, good. Moving on to C70. C70. Let's see. C70 is there. Once again, the cursor is not visible, so C70 there. C70 is fine. Didn't I review this already? C7. Alright. Okay. Yeah, I think I reviewed this C70, but I forgot to mark it as green. C71, C72. Moving on to C71. C71. These are the 10 picofarad capacitors. They should have been greened already. Both 71 and 72. Okay. C73. Moving on to C73. C73. So that's the bypass capacitors for the sensors. So 73, 74, 75, and 76. Can this be moved? Yeah, this can be moved. Let's see. This can be moved. Then we have these. C78. Okay, so they're all 2.2 microfarads. Let's see. We can say that 73, 74, 75, 76, 77, 78, 79, 80. So anything from 73 to 80 is supposed to be the same capacitors, and they can be greened right away. Now we have C8 as the next capacitor. C8 is connected to VCC, it's 50 volts, that's fine. That's on the switch the bouncer IC. We can green that one. So what I'm gonna do is I'm gonna finish the capacitors, and then I'll stop this video, and I'll continue with the diodes in the next video. So C81. C81 is connected to 5 volts, which is fine there. So got that one. Let's clean that one. Come on. Oh, god damn it. Did it just hang? Yeah. C82. Like C82 and C83, that's interesting. That's 100 volt. C82. Did I use the wrong capacitor again? Oh, I definitely did. This is ridiculous. So C82 and C83, they're supposed to be 50 volt capacitors. So let's change them. 100 nanofarads, 50 volts, 402. Field values as well. No. Validate. Update field values. You gotta be fucking kidding me. What is this? I've updated it, but I'm not getting new field values there. Ew. What did I just do? Did I reset field properties? Okay. Apparently that was like cancel. That had the same functionality as cancel. Yeah. KiCad surprises me sometimes. So, what if I update the field values like this? And then, yeah, now it's updated. So C82 and C83. I think 83 is here. Yeah. Although, let's check this. Let's just double check this. So VREF2. I'm pretty sure that this is 3.3 volts. Yes. VREF1 and VREF2. Okay. So this is definitely not supposed to be 100 volt capacitors. And large ones at that, like 6L3. Nanofarads, 402, 50 volts, there we go. Okay, and yeah. So 82, 83 can be greened. 84. C84. That's the GVDD. That was supposed to. Okay, so it's CP1. This one is 100 volts. I have to check this actually because I'm not sure what voltages are there. GVDD. Should be placed. Okay. There should be voltage levels somewhere, like a table containing voltage levels for GVDD. Internal gate driver voltage regulator. GVDD cap should be connected to ground. Okay, so 13 volts on the GVDD. Having a 16 volt capacitor is maybe not quite the optimal solution here. So maybe we could, yeah. Although the 100 volt part is a lot bigger. And this was the maximum voltage, so it's highly unlikely to go beyond 13.5 volts. So we should be okay with that. And CP1 and CP2. What is that? So CP1 and CP2. Doesn't say any voltage there. Maybe we have, let's see here. So charge pump, Is this running from GVDD, or is this running from something else? Like, what would be the voltage at the charge pump? And this is, let's see, 22 nanofarads. We have 50 volts. We have 402 there. So this one is actually a little bit of a question mark. What I could do actually is I could find some reference schematic for this chip. Let's see, DRV 8302 reference schematic. See if I can find something. There is something there. Okay. It doesn't really say. What about yeah? It doesn't really say what voltages those are. So going back to the data sheet, what would make sense here? So charge pump regulator. I mean, it would kind of make sense that this will never go beyond 13.5 volts anyway. Except that what will happen here is that this capacitor will be kind of connected between the PVDD and the charge pump output. So, okay, but this is also, what is it used for? Let's see. Three-phase, let's see. It doesn't really say, so I think I'm gonna leave it at let's see. Yeah, this one is a C89. Let's see here. Let's green C84 and C89. We can make it yellow, because I'm pretty sure that this 100 volt rating will is going to be more than enough, but I think that it's possible that I could use a smaller capacitor. I could use the 402 version, and also I think I'm using 402 22 nanofarads somewhere. I'm not sure where though. But if I'm gonna go back to these capacitors, and I'll see if I can do something smart about them. For now, I'll go to C85. So C85. Let's see. Oh, what is this? This is interesting. Make that horizontal line. Let's see. There we go. So C85 and C90 is exactly the same story. Let's see. Place that there. So C85 can be green, and C90 is yellow, and C86 is VDD33 bias, which is 402. VDD bias, right, that's for the EtherCAT. And 87, 88. C87. That's AVDD. And AVDD maximum voltage is how much? GVDD. I'm gonna search for GVDD because I think I can find it quicker. Or maybe not. Maybe not. Is there AVDD maximum voltage? Maximum voltage is 8 volts for the AVDD, which means we can use a 10 volt capacitor. Even smaller margin, but yeah. So is it reasonable to use, okay, so typical is 6.5 volts. Is it reasonable to use maybe 2.2 microfarad capacitor? That would be nice. If I could avoid using the 1 microfarad. I'm gonna make this one yellow, because I think these ones can be also replaced. So 87, and the other one was called 88. Yes, good. So C9 then. C9 is 50 volts, that's fine. That'll be green. C91. C91. DVD. So this is also something, let's see. We have the kind of back here, let's see. No, let's go forward. DVDs, 3.6 volts, yes. So this is also, I'm going to mark those as yellow as well, because I think I will actually replace them with 2.2 microfarad capacitors, 16 volts, the ones that have 402. I think that's reasonable. Actually, I might as well do it now, because I think I'm gonna just check if I use the 1 microfarad anywhere else. Let's see. Yeah, they're only used there, and this is completely unnecessary to have just 4 capacitors when we are using many of the 2.2 microfarad capacitors. So I'm going to replace all of them with 2.2 microfarad capacitors. Let's see. 2.2, 16 volts. Like that. And like that. So optimizing the bill of materials a little bit. And like that. And like that. Excellent. Update field values. Okay. And going back to the list here. So we can green all of them. 91, 92. That's great. And then we have just a bunch of bypass capacitors, probably. 93, 94. Let's see here. C93. Yeah. 93, 90, where's 94? 93, 94, 95, 96, 97, oh, 97 is connected to the back EMF, op-amp, 98 is connected to the other back EMF op-amp. Let's see. Take this. 99, 100, 101, 102, 103, 104, 105. Yeah. Actually, 105. And what the hell is this? They're not even there. That's like, what the hell is going on here? Did it? No way. No way. God damn it. Does it? Let's see here. Okay, keep existing annotations. So why is it that I don't have the 105? Like nothing beyond 93 is here. Interesting. So we can green those, but like, where are the rest of the capacitors? Let's see. Do we have the rest of the capacitors here? Nope. Okay, so I'm going to close this one. I'm going to open up the file again. So this should be, let's see. Oh. Okay, yeah. I'm an idiot here. So because of the sorting, because the sorting is done with using text, so it's not really a number sorting. I have to improve my Python script to sort all of this stuff correctly. But because of that, all of the 100, everything beyond 100 has ended up higher up. So we can just close this, and we can just make sure that that's the case, which probably is, yes. So we have up to 157. So anything, yeah, I already greened them all. So that's it. That's it for the review of the capacitors. And moving on in the next video with the review of the diodes. Thanks for watching.